So thank you very much, Alex. I'm going to have a little departure here from the first two speakers. Professor Oberdorster talked about essentially rats versus humans using lung burden analysis and overload. And Professor Grime talked about pretty much the rat issue without talking about humans. And I want to introduce the issue of risk here as well as hazard. Just in terms of background, we've known for some long time that overload concentrations and poorly soluble particles in chronic overload assays produce lung tumors in rats for a variety of particle types. And these lead to ultimately setting occupational exposures, particularly if we're using a hazard approach. Now, recently, as has been mentioned in the previous two talks, the ANSYS in their CLH report concluded that TiO2 particles should be classified as a category carcinogen 1B by the inhalation route. And category 1B is applicable to the substance presumed to have carcinogenic potential for humans based largely on animal evidence. But also in that document, and the blue is my comments, although no definitive conclusion can be drawn about the carcinogenic effect after inhalation of TiO2 based on human data, and I would disagree with that because there are a number of negative epidemiologic studies, which I'm going to touch on briefly, but will be explained in much greater detail tomorrow. Lung tumors were reported in 2 inhalation studies in animals with Lee et al., as we've heard in actually both reports, and as well as the anatase through TOP25 TiO2 study by Heinrich in 1995 and coworkers. Now, according to the documentation in the Lee study, performed with a protocol similar to OECD guideline, the increases of adenomas were reported in both sexes. Now, in their documentation, ANSYS refers a lot to IARC and NIOSH, I would say the 2 main organizations. However, in my opinion, the authors did not recognize the significance of the NIOSH CIB Current Intelligence Bulletin executive summary of their report, which was published a few years ago, where NIOSH wrote that the 250 milligram per meter cube level, which was the only level that produced tumors in rats, was an excessive dose and should not be considered relevant for human risk assessment. And this is in their executive summary. According to NIOSH, however, exposure concentrations greater than 100 milligrams per meter cube are generally not considered acceptable inhalation practice today. Keep in mind that the 50 milligram per meter cube, which produced a huge lung burden as demonstrated by Professor Oberdorster, did not produce tumors. Consequently, in a weight of evidence, according to NIOSH analysis, NIOSH questions the relevance of the 250 milligram per meter cube dose used for classifying exposure to TiO2, which was a prominent example in the ANSYS document, as a carcinogenic hazard to workers, and therefore concludes that there are insufficient data at this time to classify TiO2 as a potential occupational carcinogen. Moreover, I would say that the Heinrich study would not be viewed as a guideline study. It was one satellite group that was used for PAH and I think diesel carbon black, and does not conform to dose response OECD guidelines. So some of the brief responses, and I'll get into these in much greater detail, is that the formation of tumors upon inhalation to TiO2 is considered very specific to rats, and I'll explain why, and limited to conditions of particle overload. Species specificity itself, by a complete absence of similar responses in all other tested species, and we're going to talk a little bit about not only comparing rodent species, but primates and even humans and particle distribution characteristics, coupled with human negative epidemiology, suggests a lack of relevance to this observation in humans. In addition, this disposition of inhaled particles has been shown to be substantially different, and I'm going to show you why, between non-human primates and rats, and also humans, with the latter being particularly sensitive, that being the rat. And finally, the lung cellular responses of rats exposed chronically to particles is hyperinflammatory and hyperplastic, and these were studies done in the 80s and 90s, while primates show normal physiological responses, such as particle accumulation and macrophage responses. Enough of the reading. I want to get to some of the issues now. And essentially, I'm focusing on a weight of evidence issue. And this includes what I would call risk. That has to do with exposure and the difference in species. So focusing on weight of evidence and what I'd call fit for purpose, looking at we really are trying to protect humans, not rats. And I think lots of times that issue is forgotten. So the outlines of evidence that I'm going to talk about very briefly, because I have a limited amount of time, is talk about first interspecies differences in lung response of rats versus other rodent species. Look at the studies that have been done between rats and monkeys showing differences in particle distribution patterns and also the responses. And focusing also on the differences in pathology of why tumors in rats are different than tumors in humans. First of all, we don't have a good comparison because humans do not develop tumors to PSPs, which Professor Oberwörster, I think, referred to as PSLT, but I'm going to talk about it, same thing as poorly soluble particulates. So we have to rely in humans on things like asbestos and cigarette smoke, which are the, although not very good comparisons, the only areas where we can look at, and Professor Schultz will talk more about this later. And I'm going to talk about the difference in morphologies of these tumor types very briefly, and then focus on, very briefly, the comprehensive epidemiology studies of more than 24,000 workers, high production workers, TiO2 workers, who we presume are the most heavily exposed individuals. So how do I start with the first initial comparison of interspecies differences in rodent responses? Before I even look at this table, I don't know how to work this, but essentially, there have been a number of chronic inhalation studies in rats, mice, and hamsters, primarily rats versus mice. And in every case with poorly soluble particulates, rats develop tumors, mice do not. This has to do with carbon black, has to do with titanium dioxide, and with talc. Probably some others, but I'm focusing on those. Now, what has been, I think, revealing in the last 10 years are the subchronic inhalation studies done by Bermudez and Elder, where they exposed rats, mice, and hamsters all to the same particle types, all same concentrations for 90 days, and did what I would call a series of mechanistic studies to look at what are the mechanisms involved in trying to demonstrate why or why not the rats get tumors and the mice and hamsters do not. And I think that in these 90-day studies, they're very revealing, and I'm going to talk more about them, and that's the basis for this table. So likelihood for developing particle overload in the rat is high, and interestingly, in the mouse, in all three of those studies, it was high as well. The mice, but not hamsters, developed particle overload. So we almost have a good way of comparing the responses. But in the rats, they move on, and I'll show you a little bit later, to this so-called pathologic sequelae. I'm going to call it the adverse outcome pathway conceptual or mechanism, whereas the mice, starting out with the same level of overload, do not develop these same physiological or physiopathological parameters. They develop overload and inflammation, but do not go on to cell proliferation, metaplasia, secondary genotoxicity, and ultimately tumors. The alveolar macrophage responses for the rat and the mouse are high, including the hamsters. The pulmonary inflammatory response are similar for the rats and mice, but that's where there's departure. The degree of alveolar epithelial cell proliferation is high in the rats, but medium to low in the mice for all three of these studies, and the location of retained particles in the lung for these species are all in the alveolar ducts, and this is going to become important in a few minutes. So bottom line is the development of particle overload related tumors in the rats occurs, but not in the mice or hamsters exposed to similar or identical materials. So this is a, I don't know how to, so I'll use my own. This is a graph that I published many years ago. This is the beginnings of particle overload. I'm sorry you can't see that on there, but essentially, this is after just 4 weeks of exposure, recapitulating the Lee study from '85, showing that after 4 weeks, you get a very significant difference between the 250 milligram, this is the amount of dust in the lung, up to 180 days post-exposure. So you can imagine what it looks like after 2 years of exposure. Essentially, there's a huge accumulation of TiO2. Even in the 50, there is a particle overload, although it doesn't produce tumors. Now, another very important issue when we talk about rats versus primates is that in the rats, all of the dust, for the most part, particularly until you get to 2 years, remains in the alveolar region. This is alveolar duct region. This is a light micrograph of lungs of rat exposed for 4 weeks to 250 milligram per meter cube of TiO2. And you can see here that most of the dust remains in the alveolar duct, actually within macrophages, but does not move to the interstitium. A higher magnification of this seen in this micrograph. And you can see here there are dust, TiO2 dust, after 4 weeks of exposure that we took. And actually it resides in macrophages. This is a transmission electron micrograph of a macrophage full of TiO2 particles adjacent to an epithelial cell. So this becomes critical information when we compare rats to monkeys or humans. After 2 years, the dust becomes more distributed, and this, you can see this lung is virtually full of TiO2. This is at 250 milligrams per meter cube that ultimately produce benign tumors. But another interesting issue that will be discussed much later in the pathology section is that only the rat develops what's called keratin cyst, proliferative keratin cyst formation. You can see the TiO2 dust. These are strange looking to me, proliferative keratin regions. You never see this, not only in other rodent species, you don't see these in primates or in humans as well. So the ESITOC task force has produced what's called a conceptual AOP, adverse outcome pathway, which is a simplified version of what happens in the rat with impaired clearance. Key is persistent neutrophilic inflammation leading to cell proliferation, genotoxicity, a variety of fibrosis, and a variety of other factors, including metaplasia and bronchoplasia, not mentioned here, that ultimately leads to tumors. The interesting thing for rodents is that the mouse also, after impaired clearance, develops persistent neutrophil inflammation, but essentially very small cell proliferation. None of these other pathologic sequelae take place in the mouse, even though you have a nice comparison of impaired clearance and early inflammation and persistent really throughout the study, the 90-day study. So there's a real difference between the rat and the other rodent species. Now, when we move to compare the effects of rats versus primates, and I'll talk about humans in a minute, there's, as I said, the likelihood for developing particle overload is high in the rat. It's not determined in the human and primate. The alveolar macrophages responses are high in the rat's accumulation, I showed you a minute ago, in the alveolar ducts. but they're not extensive due to greater particle translocation to the interstitium, and I'll talk about that in a minute. The pulmonary inflammatory responses are much higher in the rat than in the monkeys. And the location, and this is critical, is the rat keeps most of it, for some reason, of its dust within macrophages on alveolar ducts. But in primates and humans, much greater than 50% of the inhaled dust translocate, that is, move from the alveolar compartment to the interstitial compartment, some within interstitial macrophages, others just in the interstitium, and I'm talking about the studies that demonstrate this. So the development of particle overload related tumors in rats, of course, is yes, but in primates and in humans does not occur. Now this is a picture of a light micrograph that I borrowed from Dr. Jerry Abraham of interstitial-based coal workers' pneumoconiosis. And the key feature I want to describe here is that the dust, although it's not as evident here in this low-level micrograph, is interstitialized throughout the lung, not only alveolar, but a lot of that is in the interstitium. This is going to be important in a minute. So we have to go back almost to the 80s and 90s to look at studies which compared exposures to rats and monkeys in the same study. Now I realize that 2 years is a lifetime of a rat and it isn't for a monkey, but I think they're pretty revealing. So this was 1987 petroleum coke. Essentially the rats at fairly low concentrations. These are non-overload experiments. So chronic inflammation, focal fibrosis, alveolar metaplasia, keratin cysts in the rat. In the monkeys, there was just essentially black discoloration described, deposition and phagocytosis of normal test material. This was back in 87. McFarlane in 82 exposed rats and monkeys to the same concentrations of raw or processed shale for 24 months. And we get the same pattern: proliferative bronchiolitis, fibrosis, microgranulomas, pigment-laden macrophages in the monkeys, essentially little or no adverse reaction. Similar was found with the Lewis et al. And Nicula et al. Studies with diesel and with coal dust. And I'm running out of time, so I'll finish. So Nicula, and to me this is a very important study, did a morphometric study of humans versus rats. Rats exposed to diesel exhaust, humans exposed were non-smoking coal miners or exposed coal miners. Bottom line is that 82 to 85% of the retained particles in the alveoli were in rats, primarily in macrophages that I showed you. But in humans, the chronically inhaled particulate matter retained was primarily greater than 60% in the pulmonary interstitium. And the epidemiology studies, which will be covered later by John Fryzak, are all negative, so I won't go into detail here, but this covers over 24,000 workers, which we believe are the highest exposed individuals. And this is not just unique to TiO2, carbon black. Bob McCunney will talk about those. Talc and coal dust, May Young will talk about those. No correlations with occupational exposures and development of lung cancers. So when we consider rats versus humans, there are 5 factors. And by the way, we just had a paper accepted this week, which will be available to send to reprints for anybody who might want to have me send it to them, talking about these 5 factors which separate rats from humans. And these are, as I talked about, interspecies differences in particle kinetics of rats versus non-human primates, rodent interspecies differences, advanced updated ICRP models which show greater translocation to the interstitium, comprehensive differences in the pathology, which Professor Schultz will talk about, of, that's down here, of the tumors in rats versus humans, very different locations, and also in-depth analysis of the epidemiology data. So the conclusion is that the most plausible conclusion we can reach is that the studies in particle overloaded rats are not relevant for humans in a working lifetime to poorly soluble particulates. And in the last minute or two, I'm just going to talk about differences in the microdissection. If we look at the rats, these are scanning electron micrographs, we see that particles deposit primarily in the alveolar duct bifurcations. As we move, this is the terminal bronchiole, alveolar duct bifurcations. And macrophages occur, phagocytize the particles, and move down the mucociliary escalator. But in humans, we have not only a different proportion, but most of the particles deposit in the respiratory bronchioles, which are a little bit different than the alveolar duct bifurcations. And also the tumor types are significantly different. So Acetok concluded that the rat represents a unique and particularly sensitive model. All the things that I talked about, including epidemiology studies, and more importantly, particle distribution and retention from rats versus humans and primates are very different. So these are the 5 factors. Again, we had a paper just accepted, which will be available to send reprints in the next 3 or 4 weeks. 5 different factors which we think separate the rat responses from the human responses. And these are later questions for the audience, but I want you to think about them now. What does it take to prove a negative response in humans? What would it take if we're dealing with risk versus hazard? How should hazard versus risk be handled? What if the mechanisms of action truly are different between rats and humans, primates? And how should the precautionary principle be implemented, or is it appropriate? Thank you for your attention.
This really is science in action, isn't it? And of course, many of the things Dr. Warheit was saying, also going back to some of the points that you made, Professor, on particle retention, different animals. We'll come back to all of that after the coffee break.
Yeah, sure. Now, okay, well, I think there is agreement about the mechanism and the underlying mechanism. My problem is because we have to derive a value at the very end. Where is the OEL? Where is the NO observed effect concentration? And the problem is that there are a lot of studies with slight changes in this sputum, in BAL, in bronchoalveolar lavage, with changes in leukocytes and myeloperoxidase and so on. And the question is, what is an adverse effect and differentiated from a just adaptive effect? You know, that is the issue for deriving an appropriate no observed effect concentration.
Okay, thank you very much.